Hello, this is my fifth lecture, and today we shall discuss about the electrostatic potential energy of a system of two charges. When two charges are separated by a certain distance, consider Q1 and Q2 are the two charges separated by a distance r. Then the potential energy of the system will be the work done in displacing either charge from infinite to this distance r is equal to the electrostatic potential energy of the dipole. Electrostatic potential energy of a system of two charges separated by a certain distance is work done in displacing either charge from infinite to certain distance, from infinite to certain distance against electrostatic force. So electrostatic potential energy is the work done of either charge in displacing from infinite to certain distance. In this case, consider two charges Q1 and Q2 separated by this certain distance small r. Separated by certain distance small r, and Q2 is displaced from infinite to distance r, and Q2 is displaced from infinite to r. Then work done W is equal to integral charge is displaced from infinite to r f dot dr. W is equal to integral f dot dr. This is the work done in displacing either charge from infinite to certain distance r. Now, integral infinite to r f dr cos 180, and value of cos 180 is -1. So W is equal to minus infinite to r f dr, and value of infinite to r, because here in this case both charges are positive. So if either charge is displaced from infinite to this distance r, then displacement and force are perpendicular, opposite to one another. So we considered cos 180, and F is equal to, we know that K Q1 Q2 upon R square dr minus K Q1 Q2 integral infinite to R power minus 2, this minus R is 1 upon R square is displaced, and dr. We know that the formula of integral x and dx is equal to xn plus 1 upon n plus 1. Let's say integral comes, right? So have that integration of work done W is equal to minus K Q1 Q2 R minus 2 plus 1, because the formula is xn dx is equal to xn plus 1 upon n plus 1 upon minus 2 plus 1 from infinite to R, or W is equal to minus K Q1 Q2 and minus 1 upon R infinite to R, or W is equal to, this minus can be taken out, so K Q1 Q2 1 upon R minus 1 upon infinite. The value of 1 upon infinite is 0, so the work done in displacing the charge particle will be K Q1 Q2 upon R against the force, and this work done will be stored in the system of charge particle in the form of potential energy called electrostatic potential energy. UE is equal to K Q1 Q2 upon R. This is the potential energy of a system of two charges. If the variation is considered just U and R, the value will be hyperbolic. The shape of the curve will be hyperbolic. And if the system of two charges, both the charges contains positive or negative charges, then the potential energy will be positive. And if one charge is with positive sign and other one is negative charge, then the system of charges will be, or the potential energy of the charges will be negative. So this is the potential energy of a system of two charges. Had we considered both the charges of positive nature, if both the charges are with positive sign or with negative sign, the potential energy will be positive. And if one charge is positive and other one is negative, then in this case the potential energy will be with negative sign. So this is the potential energy. If we consider a charge, a system of charges with three charges, Q1, Q2, Q3, the separation of Q1, Q2 is R12, the separation of Q1, Q3 is R13, the separation of Q2, Q3 is R23, then the system potential energy of the system of three charges situated at the vertices of a triangle will be, the potential energy will be is equal to K Q1 Q2 upon R12 plus K Q1 Q2 upon Q1 Q3 upon R13 plus K Q2 Q3 upon R. If a triangle is given to us, then the potential energy can be calculated just like that. K Q1 Q2 upon R12 plus K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. This is the potential energy of a system of three charges, and all the three charges are situated at the vertices of a triangle, and if the system of four charges is considered and all the charges are situated at the vertices of a quadrilateral or a square, in this case the charges are Q1, Q2, Q3, Q4, and this distance is R12, this is R23, this is R34, this is R41, this distance is R42, and this distance is R13. If the distances are equal, then we can consider the equal distances, and if the distances are separate, then different, then we consider then the potential energy of the system of these four charges is equal to the potential energy U is equal to K Q1 Q2 upon R12 plus K Q2 Q3 upon R23 plus K Q3 Q4 upon R34 plus K Q4 Q1 upon R41 plus K Q1 Q3 upon R13 plus K Q1 Q2 Q4 upon R24 or 42. So, in this case, there are 6 steps will come, and for a triangle, the 3 steps are come, and for a 4 system of particles, the 6 steps come. U is equal to the total potential energy of the whole system of 4 charges situated at the vertices of 4 quadrilateral or square or rectangle, then K Q1 Q2 upon R12, this one, K Q2 Q3 upon R23, this distance, Q3 K Q3 Q4 upon R34, this distance, and K Q4 Q1 upon R41, this distance, and also we consider K Q1 Q3 upon R13, this distance, and the diagonally charges are also considered, plus K Q2 Q4 upon R24. So this is the potential energy of the system of charges contains 2, 3 and 4 charges. Now we shall discuss about the superposition of electrostatic potential of a system of charges. Superposition of electrostatic potential of a system of a particle. If a particular point is under the influence of a number of charges, then the net potential on the charges will be the algebraic sum of all charges that has influence at the point. So for the purpose, this is a small topic, and today we shall discuss this topic, and tomorrow we shall discuss about some questions based on these 2 topics. Consider a point O here and a system of charges Q1. This distance is R1, Q2, and the distance is R2, Q3, and the distance is R3, dash, 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 and Qn, and the distance is R. A system of charges has influence 8.0, and if we want to calculate the potential at this point, then we determine the potential due to individual charges at point O, and then the potential due to Q1 charge. Q1 V1 is equal to KQ1 upon R. Similarly, potential due to Q2 charge V2 is equal to KQ2 upon R2, and dash 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 potential due to Qn charge will be is equal to Vn is equal to Kqn upon Rn. These are the potentials of individual charges, and then the net or total potential will be the algebraic sum of charges, because the sum of potential due to a positive charge will be taken as a positive sign, and potential with a negative charge will be taken as with negative sign. So there are two kinds of potential. So net potential at point O. V is equal to V1 plus V2 plus dash 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 Vn. Potential is a scalar quantity, so it is not need not to put the vector sign. So V is equal to Kq1 upon R1 plus Kq2 upon R2 plus dash 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 Kqn upon Rn, or V is equal to summation I is equal to 1 to n Kqi upon R. So if a charge is under the influence of a number of charges, then the net potential will be the algebraic sum of all charges. If a point is under the influence of a number of charges, then the net potential at the point will be the algebraic sum of all charges, algebraic sum of potentials due to individual charges, So this is the potential of a system of or superposition potential due to a system of charges or a number of charges at a certain point.